Bond enthalpies. We've done Hess's law. We've done Q equals Cm delta T. We've done all the fancy formulas. But now it's time to get out your pocket calculators, to get out your pencils, and to do it the hard way. Yes, the hard way. Because bond enthalpies is the way that you can calculate the change in heat. It takes more time, takes a little bit more work, but on the other hand, it's purely theoretical and it requires no experimenting. Except for the guys who figured out the original bond enthalpies, but they don't count. It's literature values now. So, the idea of bond enthalpies is that to break bonds is an endothermic process. Endothermic process, what does that mean again? Remember, your heat goes from boo to boo, which means the amount of heat in the bonds or in your molecules is going to end up having to increase. You have to put heat in to break bonds, which makes sense when you think about something like breaking water. How do you break up water into hydrogen and oxygen? You have to use electrolysis. And electrolysis means that you're introducing energy to your system. And the rest of bonds are just like that as well. So, breaking bonds is an endothermic process, which means bonds themselves have positive enthalpy or negative enthalpy. A bond, when two atoms bond together, the amount of heat total is reduced because they will then go and release heat. They're more stable. They don't need as much energy to just hang around, which is really nifty when you think about it. But the idea behind this is that when you take your average bond enthalpies, and when you know average bond enthalpies, for example, a bond between two oxygen molecules, two oxygen atoms, and oxygen and hydrogen, you can then figure out from adding all of your bond enthalpies together, the enthalpy of a particular molecule. For example, taking an example of H2O. If you look at the bond enthalpy of the OH bond, it is listed as being plus 463, which is going to be in kilojoules per mole. So when you look at that, you say it's going to take 463 to make one bond. If you look at the structure of H2O, you have your O in the middle, two H's each connected by a single bond. So you're going to know that's going to end up in the end being 926. Okay? So you add them together because you have two OH bonds, so you just multiply by 2 and you get 926 kilojoules. That's going to be what it takes to split H2O into its component parts. Thus, what you can do is create this kind of step-by-step look at a reaction, which says, instead of looking at a reaction as if you're looking at the reaction of methane plus oxygen to carbon dioxide and H2O, when you're looking at that, instead of looking at it as CH4 plus O2 becomes your CO2 plus H2O, we can look at it as CH4 plus O2 will then become C plus 4H plus 2 O's will then become, of course, you already have all your component parts, so then it will become again your CO2 plus H2O. Okay, well, plus 2H2O. So when we're looking at this, you're saying, okay, why are we bothering breaking everything down all the way and then rebuilding it? And the reason why is if you break it down all the way, you can figure out the bond enthalpies for every bond. So taking that example of methane plus oxygen will end up creating water and carbon dioxide. When you look at methane, chart it out using your wonderful Lewis diagrams, and you'll see it's a carbon surrounded by 4 hydrogens, each bonded by a single bond. The carbon-hydrogen bond has a bond enthalpy of 414 kilojoules per mole. So you know that your bond enthalpy for the entirety of methane is just 4 times that, which will end up giving you 1656 kilojoules per mole. Okay? And then for the oxygen, remember, we talked about earlier the idea that diatomic molecules don't really have a bond enthalpy. It's the same here. Oxygen will come together with oxygen with no other energy required. So there you have your bond enthalpy of 0. Then when you look at it with the idea of CO2, which is going to have two double bonds between carbon and oxygen. So that's 2 times 804, because double bonds are pretty strong. So it's 804 kilojoules per mole, which will give you 1608, plus your water, which I do believe we already calculated to be, where we already calculated the water, that's going to be your OH, and your OH bond is 463, so your total bond for water is going to be 526. Okay, so we know that. And this we'll be able to find our total bond enthalpies for the reactants, total bond enthalpies for the products. Okay? And when you look at your total bond enthalpies for your reactants and your products, you could then just subtract total bond enthalpies for reactants from your total bond enthalpies for products, and you're done. You're done, you're finished. Peace out, homies. And that's going to give you your total enthalpy of reaction in kilojoules per mole. Nifty schmifty, there you go. Now, a useful application of this, and I'm going to give you down the simplified version more or less, the idea of having your bond enthalpies and breaking these bonds and the strength of bonds is the idea of ozone depletion, which is currently a problem because ozone has a tendency to be in our atmosphere. And what ozone does is it will then absorb the infrared radiation, which is coming down from the skies, and not infrared, ultraviolet radiation, and it keeps that set of radiation from arriving on our planet's surface and baking us, like wee little Brussels sprouts in a microwave. And we don't want to be wee little Brussels sprouts in the microwave. So essentially what happens is that with oxygen, you have a single double bond. And a single double bond of oxygen requires 498 kilojoules of energy to break, whereas a single bond of oxygen requires a measly, not listed amount of energy to break. This is why you want really thorough tables, because the downside of bond enthalpies, if you don't know all your bond enthalpies, well then, okay, you're not going to be able to figure it out. But know that it takes less energy, okay? So the idea is that because ozone, the setup of it is that it's a molecule that has both a double and single bond, it requires a different amount of energy, whereas diatomic oxygen only has a double bond. Because of this, ozone can absorb different levels of UV light, and it allows for a wider spectrum of UV light to be blocked coming through the atmosphere. Thus, when we have our ozone being destroyed by, chlorofluorocarbons and such, then you only have your normal oxygen, your O2, instead of your O3. When you only have your O2, what ends up happening is that the UV wavelengths that would sometimes be getting absorbed by the single bond are no longer getting absorbed to the same degree, and because of this, UV rays are coming through to Earth, and because UV is a very high energy ray, it can cause things like wonderful skin cancer and such. That's why I have to put on sunscreen. But it can also cause global warming because a greater amount of energy is getting through the atmosphere. And then it gets trapped within the atmosphere again by the rest of the gases hanging around up there. So there you go. That is why bond enthalpy is important. Remember with bond enthalpy, the stages, or you have your reactants, break your reactants down into the atoms, and figure out what bonds were broken there. Then you rebuild them back into the products, figure out how much energy it took to do that. Products, bond enthalpy minus reactants, bond enthalpy, whoop, and then that'll give you your your enthalpy of reaction. And there you go. Have fun doing enthalpies the old school way.